Hey guys. Today there's round 731. I think everything's gonna be great. There are new authors. Actually, I don't expect that to be great, but I guess we'll see how that goes. I'm not gonna touch my mic anymore. I have the wiring like in the back. There's hopefully no way I can like mess with it again by accident. So I'm prepared this time after what happened in the last video. And yeah, we're actually on time for once. So let's get this started. Um, okay, so that's annoying. Um, okay, so only if a0 not equal to a2, a1 is not equal to a3. So in the case where we don't have to go around, that's fine. So if a0 is less, so assume one coordinate is less than the other. So then see out. So if this is equal to that, then okay. There's a fun problem. Alright, right? So the initial answer is the distance between them. Now, if they're both unequal, then it means we can take any path, and so the answer is just the answer. Otherwise, if the x-coordinates are equal, then if the other thing is also between them, then we need to add 2, and we check the same thing for the y-coordinates, I guess. Yeah. Alright, that's a pain. Good, I'm glad I'm done with that problem. Okay. String length n. Write an empty string to s. Okay. I don't know why I didn't do this in the first place. Pause si minus a. Okay, so if count I is greater than 1, or done and count I is greater than 0, val is equal to 0. Alright, so if count I is greater than 1, if we have more than one of a character, or if we're already done, because we have to have like a prefix of the characters, and if we're done and we still have something, yeah. L is equal to pause 0, R is equal to pause 0. If count I is equal to 0, break. Pause I plus 1 is equal to L. And pause I minus 1 is equal to R. L is equal to 0, break. Alright, so annoying so far. Yeah, I can't say I'm loving this, but it is problems. So we're checking if at every point they form a continuous subsequence. At each point we can either extend the string to the left or to the right. So we keep the counts. If we have more than one of any character, or it's not a prefix, then it's impossible. Otherwise we start making the interval. Pause I plus 1. Yeah. Okay. Pair programming. What the hell are these statements? Oh my god, this is so long. Okay. N plus n minutes. Each minute exactly one of them made one change to the file. For the start, there are already k lines. Adds a new line, it changes one of its lines. Great, okay. So we want to add whenever possible is okay. Okay, so that's fine. C into K to M to M. C into AI. Okay, PA equals 0, PB equals 0. And pause equals 1. Okay, so if PA is less than N and let's see, APA is equal to 0, then plus PA plus K. Else, if PB is less than M, BPB is equal to 0. Plus PB plus K. Else, so if PA is less than N and it doesn't really hurt to do greedy, because doing an operation doesn't really hurt us. PA is less than N and what? and A, PA. Oh, wait, actually, it's just this. It should be less than or equal to K. Yeah, this should be easier. Okay. If pause cool. So it's basically greedy because picking any operation doesn't really hurt us, so we might as well do them in any order that's valid. Actually, don't really understand the point of this problem. 2005. Yep, this is the only way. 20506. Yeah, that's fine. Into AI, C into BI. Okay. Alright. Cool. Sequence of non-negative integers. Let's consider growing. Oh, okay. So super submasks. Co-growing. Okay. Two to the 30th. Well, okay, so it has to start with 0, of course. Now, okay, cool. This one's actually not a pain to implement, which is awesome. So let's see. We need the bits that are missing. And it's equal to, what is it? So it's cur minus I think that's right. I'll explain this all later, of course. Oh no, okay. Cur is equal to yeah, right. So it's everything in cur minus the stuff we already have. Yeah, we can't do better than that. So that's lexicographically smallest, right? Yeah. Okay. Strip of length n, there are k air conditioners. Right, the air conditioner is placed in cell AI. Cool. C into CI, minus BI, ACI is equal to BI. Nope, wrong way around. ABI is equal to CI. AI is equal to 289. I have long ones, right? Yep, okay. First we sweep left, so R is equal to 289. And 289. CI and psi is equal to pulse plus R. We do the same thing here. Okay. How? Oh wait, AI, not CI. Yeah, seems good. Right, so we're going left and we're going right. C into BI, C into CI, minus BI. It's one indexed, so that's okay. Then ABI is equal to CI. Now ants, initialize it to 289, that's fine. Then, yeah. Sorry, I'm trying to speed run right now because I'm usually doing that for div 3s. But yeah, basically we're sweeping left and then we're sweeping right. Because we know the air conditioner is going to be to the left, it lets us break the absolute value condition, which is nice because that's sort of what we want. Is this going to penalize me? Okay, I guess I will submit again. This happened to me last time too, it just like didn't submit. Oh, okay, cool. I guess that worked. Where's that put me now? Okay, we're doing pretty well. You're given an array of positive integers. In one step, the array A is replaced with another array of length n. Each element is a GCD of two neighboring elements. Also, this didn't hurt me, right? Yeah, okay. All AI must become equal. Cool. Okay. So first, we find the GCD of the whole array. That must be the final element. Since eventually the entire array will be compressed to that. Okay. Now basically we're finding out. So find the GCD of the whole array. C into AI. Well, G is equal to A0. Let's compose, right? Okay, now what do we do? Now we figure out when it becomes this. good. There's a better way than two-stack trick. So let's figure that out. We're going to find the largest subarray such that GCD is not that. How do we do that? We can do binary search, I guess. I understand. What? Oh, it's circular. Oh, wait. Okay. Okay, that's more interesting. Alright, that changes a lot, actually. Does it actually? Wait. So after an operation, index is basically set. So we're still, after two operations, this will be equal to that. One operation, everything is equal to GCD of whatever was before. The two operations, everything's equal to that. Okay, so we gotta like, yeah, I'm gonna totally overkill this, cause why not? Yeah, I'm gonna totally overkill this. 0, -1. Okay, LL point is equal to 0. So sm.push AI. Oh, there's no max, right? It's all GCD, GCD, GCD. Yeah. Now, while sm.query is greater than G, sm.pop plus point. Okay. Okay, what now? Okay, so COG. So reading the end decay, reading the array values. Here the GCD is 1. Alright, so that's expected. Oh wait. What are we doing? Find the longest. Oh yeah, this doesn't make sense. Okay, it's the longest subarray such that its GCD is greater. Oh yeah, okay. Less than or equal to. What? What's happening now? So 2, 1. I don't get it. Why am I struggling so hard to write this? This is so simple. It's so simple. What the hell? So having no elements should be fine. While sm.query is less than or equal to g. So push AI. While query is less than or equal to g, pop. Oh wait, there's no k. What am I doing? Two, 5, 2, 5, 6 minus 1? No, it doesn't make sense. No, it doesn't make sense at all. Okay. One. Oh, wait. Ants plus 1. Okay. Finally. C into AI. Yeah. Okay. Good. Finally. Makes sense. And log in. Everything should be fine. Yeah. Okay. Many paths. Okay. We're given a directed graph G which can contain loops. Path from U to V. So 150. Cool. So I guess now we're doing SCCs. Alright, that's at least interesting. So C into N. It's like a template contest instead of other things, which is fine. I'm okay with that. Okay, so actually no, this doesn't make sense. I'm gonna put this up here like I always do, which I'm not doing for some reason. Vector LO. Okay, 4. C into X to Y, minus minus X, minus minus Y. Gx is equal to, no, Gx dot push back Y, Gy dot push back X. Okay, wait, also, first of all, Gi dot clear, Cgi dot clear. Cgi is compressed edges. So, C dot N, C dot edge xy. Well, see, I don't do that. Ci is equal to no wait, Cx is equal to I. Now let's see. For two SCCs, if there are multiple edges between them, so if one is in an SCC at all, of size greater than 1, isn't FCC at all size greater than 1? So BI is equal to 0. Okay, now for edges CG CI dot push back. Q.pop. Okay, now we say yeah, so x equals q dot front, then we have q dot pop. If so, let's see. If ax is greater than 0, otherwise there's no point. I'm doing top of sort. Only considering that this is reachable from 1, right? Yeah, okay. This side is equal to 0. Lx, this x. DFS 1. Okay. Actually, wait, I'm going to do this. Yeah, this just makes it more complicated. Plus bx. If bi is equal to 0, q dot push I. If ax is greater than 0, okay, wait. So if the component of 0 is x, then the answer is a x equal to 1. Now, if comp x dot size is greater than 1, then if we have one path, we have infinite paths. So that's it. So ax is equal to -1. Now, for ly cgx minus the in degree of y, if ax is equal to -1, ay is equal to -1, else ay is equal to min 2 ax plus ay. Or ay is equal to -1, then do that. Otherwise, there's some number of paths to both of them, so contribute that. And if by is equal to 0, q dot push y. What? Yeah. This should be good by itself. C out, A, C, I, yeah. Okay. What's edges? It should be G. Okay, not the worst. Oh, wait. How's this work? Okay, so an SCC is special if it has an edge to itself. Wait, no, it doesn't make sense. If an SCC size is greater than 0, then it's special. Otherwise, spec I is equal to 0. So if I is equal to x, spec ci is equal to 1. What? Okay, let's see. So everything's in its own SCC here, which is expected. So now C out x, ax, so the first part, it should be where is it getting to? It's not getting everywhere. Why is it not getting everywhere? Else. Oh, if ci is not equal to cx. Okay. This shouldn't hurt. If we have any amount of edges in SCC, then it means we're fine. Yeah. So for each thing, if ci is not equal to cx, then ow. Okay. Now we should be visiting everything. 100001111. Okay, that's the last problem. CS Academy, let's go to Graph Editor. Not counting multiple paths is the thing. Corrected. Yeah, okay. So why is this happening? AI is equal to 0. That matters too. Okay, I'm gonna have to explicitly check multi-tests again. What? Wait, we're not visiting 2. Why are we not visiting it? Also, it's topological anyway, but whatever. I don't really care, it doesn't matter that much. Bi is equal to 0, q dot push I. Oh wait. That is also y. I actually don't get why that applies here, but okay. Yeah, we have to do this here. I don't get why that fixes this though. It doesn't. Why are we not visiting this? C out x, y, b, y, and O. So there's no edge from 1 to 2. And the reason is why? Okay, let's just look over code. For I equals 1 to n, clear G, CG, B, spec, and A. C is reset, so that's fine. I don't think we're using anything else. We're creating an SDC every time. We're clearing everything. C into x to y, gx dot pushback y, create an edge in the SDC, run the SDC, print the components. Now C out x. I just can't write code. I can't write code. What is happening? Why am I struggling so hard on this? It's so basic. For this, so 0, 2. Okay, so now here we're visiting 0, here we're visiting 1, here we're visiting 3. What? Alright, let's see if this is multitasking. No, okay. So we're visiting 1. Why does 2 have multiple edges into it? Why do you have multiple edges into you? Oh, that's why. Okay, good that we caught that. Good. Now we're gonna review code again. All right. So all this is pretty clear. We're resetting everything. Run the stuff for each thing. Plus b that bi is equal to 0, q dot push I. While not q dot empty, c0 is equal to x, set it to 1. If that value is greater than 0, if right, this is the part where it gets kind of weird. So for each edge, if ci is not equal to cx, make the new graph. Otherwise, that node is special, or that component is special. Now for each thing, for each component, if bi is 0, push it while the queue is not empty. If it's equal to the first component, set it to 1. Now if it's greater than 0, if we have a path to it, then it's infinite if it's special, or the component is size greater than 2, which is actually equivalent, so we don't need this, but whatever. Then for each edge, subtract it from its out degree. So if either of them are -1, then this should be -1 as well. Otherwise, both of them are not -1, so you add the paths from one to the other. One more case. 1, 5, 6, 1, 2, 1, 3, 1, 4, 2, 5, 3, 5, 4. Good. Okay. Test 8. Test 10. Come on, you can do it. I believe in you. I believe in you. Wrong answer on test 69 or something. I can see that happening. There are a lot of tests, so it's probably easy to get one wrong. Hopefully they have like brute force over all graphs of size. Like, all right, that's it. We're done. Took longer than it should have, but where are we now? All right, I'll take 9th, sure. Yeah, G took me way longer than I would have wanted it to, but this is fine. All right, so that concludes the contest. I don't think I'll drop that big of a place, maybe like 1 or 2. So these 3 people have, let's see, okay, wait, so 53 penalty, right? So I had 85 before, which means I was around here. But then, yeah, okay. So 53, it's at least 54 now, which means that someone, so these 3 have at least 92 penalty. 92 plus 54 is 136. So in fact, if he gets it right now, then he can beat me. But he didn't. So now we would tie for 9th, which is okay. And then nobody else can beat me, I think. Yeah, 93 plus 54 is too much. Oh, wait, 54. Oh, okay, yeah, nobody's even close then. Okay, good, good, good. Never mind. We're fine. Okay, this was pretty good. Sort of fell short near the end with the implementation of the last couple of problems. I don't really know, like, I definitely overcomplicated this. Maybe I'll think a bit more on how to do that, not so complicatedly. And then this was kind of annoying because it's just a lot of stuff and I messed things up and I messed everything up, so that's cool. Yeah. Alright, I don't have more to say. Some people are doing well, some people are not, as always. So it goes, as they say. Okay. I'm gonna go to the bathroom and then go over solutions. Okay, be right back. Hopefully, I'm gonna check the audio thoroughly to make sure it doesn't mess anything up anymore. Alright. So the audio is coming from not here specifically. If I touch the laptop, it doesn't increase that much, but if I touch the mic, good. Okay, I might check this more thoroughly just because, again, last video something happened. It rerouted to the laptop mic. I don't want to touch anything, so I'll check it periodically once in a while just to make sure that it's the right one. Seems like it. Okay. Yeah, unless we get hacked, which is possible. This is our final place. Seems like other people have solved stuff now, so that's pretty good. Yeah. 4. Wait, were we tied before? Oh wait, I had 84. I can't do math. Okay. I had 84, not somehow 37 minus 53 is whatever. I had 84. He must have had 85. I was beating by 1 point. That's pretty funny. Okay, I'm going to do solutions now. Actually, wait. First, I'm just going to take a bit of time and think about F. Because F was like so... Maybe there's a nicer way to do it that I don't really understand. But also people took like... Maybe it's intended to use some sort of like range query structure. Like how much time are people using for F? Varies. I guess like, I mean, my solution is n log n, or n log something, n log max value, but you can probably do it in n log, like with a log squared factor in it if you wanted. It's not that bad of a thing to do. Yeah, I mean, okay. I guess it's just a data structure problem at the end of the day. I'll treat it as that and nothing else. This has some annoying implementation, clearly. How long is this? It was 2 hours 15. Yeah, they love to do that now. Like all of the contests just have like longer than 2 hours. Like this is 2:15 as a div 2. This is that's expected. This is 2:15. This is 2:15. Why is that like? Why is that a thing? Where is this coming from? I don't understand. But whatever. Okay, I'll especially try and go over code for this. There's a possible chance that I overcomplicate everything like I often do with div 2s. I guess that can happen. Like for example, last time. Last time was just a disaster all around. I'm gonna check the mic again. And then make sure that checking the mic didn't ruin the mic. Okay. It's kind of funny. You can get like an infinite paradox. Because like if I tap the mic, maybe that does the offset thing. And then that like makes it so the mic is bad. So then I have to test it again. And then to test it again, I have to tap it again. And then when I tap it again, you know, it continues. I don't know how to fix that. I guess I'll just always be concerned about what the audio is. Alright, I'm actually kind of interested. Did people solve these quickly? I'm gonna look at, not geothermal, because that man's a monster, but maybe like, yeah, okay. It was like pretty slow for everyone. Basically the idea is you have a path. You have 2 cells, and you want to get from one cell to another. Like, for example, like this, in the shortest possible amount of time. You can only move up, right, left, or down, so you can't go in a straight line. Otherwise, that would make for a much more annoying problem. This would involve geometry, depending on how big the circles are, actually. It'd be like circle problem, which is awesome. You can copy paste our solution from mbit to that. Yeah, cool. So basically the gist is there's also a blocked cell, specifically like somewhere. So for example, maybe it's here. And you can't go through that block cell. So I, for example, cannot take this path just because it's blocked. But I can take a path like this that goes around it, for example. Or something like this. Or something that doesn't even consider it at all. Like just completely ignore it. Right? So yeah, that's the basic idea. So how does this work? We want to find the minimal time to get from like point A to point B with this metric. So how does this work? It essentially boils down to casework. So consider like x1, consider the points we have, x1, y1, and x2, y2. I'm using 1 and 2, it doesn't matter. I don't want to write A every time. So if both coordinates are different, like if x1, I'm gonna write out the decision tree here. If x1 is not equal to x2, and y1 is not equal to y2, then the answer is just the direct distance. In particular, like the difference between the x's and the difference between the y's, which is to say, the direct distance is just the difference between the x's, the absolute difference, because one might be greater than the other, and we don't want to add negative distance, and the difference between the y's. This is called Manhattan distance. It shows up a lot. It just means, like, if you consider x and y separately and then add them together, that's what it means. It's not Euclidean distance where you can, like, move in diagonals and stuff. It's Manhattan distance where you're, like, moving discretely among a grid. So, and the reason is because, like, without loss of generality, actually, we don't even need that. Basically, we always have at least two distinct x-coordinates. And the reason this is nice is because, like, suppose this is A and this, or no, we don't need that. Like, suppose this is x-coordinate 1, this is x-coordinate 2. Suppose the obstacle is not on either of the x-coordinates, then just take a direct path. We're fine. If it's on x-coordinate 1, go immediately down and then to the right. And if it's on x-coordinate 2, or sorry, these are all y-coordinates, I don't know what I'm saying. If it's on y-coordinate 2, then go directly right and then down. And this will always work because the obstacle can't be on two y-coordinates at once, so it can't possibly block all the possible paths. This strategy sort of falls apart, however, when they're on the same coordinate. So for example, suppose they're here. Then, like, there's only one case to check. If it's not on the same x-coordinate, or on the same y-coordinate, then it doesn't affect anything. Just take the straight line. Otherwise, if it is, then you have to check if it's between them, because if not, once again, we can take the straight line. And otherwise, if it is, then the best we can do is go around. And this is an extra 2 distance, because it's the straight line, except we take a detour. We go up, and then this way, and then down. So this is an extra 1 distance, and this is an extra 1 distance, so we get 2 extra distance. So basically, I think there's some nice way to do it where you can like swap the dimensions to make it so you're only checking one case. So you swap the dimensions if, like, you make it so the x's are always the same. So if the y's are the same, you swap x and y for everything, and that would work. It's not that important how you do it. It just matters that, yeah, it just matters that you do it. Yeah, so basically it's just checking a lot of different cases, and my code will do that. It will check. I'm using like array values to represent the coordinates only because I'm lazy. There's no really particular reason to do it. It's just so I can use a for loop to read stuff in. So initially, like A0 and A1 is the point A, A2 and A3 is the point B, and 3 and 4 and 5 is the obstacle. So I hope. If I read the input wrong, that would be kind of weird. Yeah. So we initially start with A0 minus A2 and A1 minus A3. So if both coordinates are unequal, if both coordinates are like not equal to each other, then immediately we get the direct distance. And otherwise we check the cases. And the way I'm doing this is I'm assuming, like, without loss of generality, that if x1 is equal to x2, then y1 is less than or equal, or y1 is less than y2. And if it's greater, then I swap them so that this is the case. And this is sort of the trick I was talking about. You can do the same sort of swapping thing with the x and y coordinates as a whole. But it's not really that big a deal. So you check if the x coordinates are the same, then you check if this is on the same x coordinate and it's between the y coordinates. And otherwise, if the y coordinates are the same, you check if it's on the same x coordinate, and if it's between the, if the y coordinates are the same, you check if it's on the same y coordinate, and you check if it's between the x coordinates. And then if any of these cases, you add 2 to the answer and then just print it. Cool, that was a pain. Yeah, kind of an annoying first problem. I think it's like, I think it's like, it should be doable for most people though. Like it has significantly more solves than B. In fact, this is a pretty nice distribution, I have to say. It's a pretty like, yeah, for a Div 3, it's a pretty good distribution of difficulty. Even G is like surprisingly tough to implement. Yeah. So let's go to B now. B is, I found it like easier actually. Just easier to like, maybe not easier to think about, but easier to code at least, just because it's not like, there aren't a million cases, so you can be more confident that your code will be correct. Basically, we're going to construct the string in the following way. We're going to start with A, then either we'll stop or we stick on B. Now, where do we put B? We can put it only either to the left or to the right of the current string. So say we put it, for example, here. I'm not going to use different colors actually, because I'm going to run out of colors. Now we look at C. Either we stop here or we put C to the left or to the right. In this case, I can put it here. We look at D. Either we stop or we put D somewhere on the string. Maybe we look at E, and now we'll stop. So we're left with this. We're given a string. We want to see if it was constructed using this algorithm, essentially. So if it was constructed in some way by starting with A, then putting B to the left or the right, then putting C to the left or right, then putting D to the left or right, etc. And so there are a lot of ways to do this. In particular, because the string is so small, a sort of like brute forcing method would work. Not like checking all permutations, of course, but it would be sort of brute forcing. Like basically, the way a brute force would work, and maybe it's actually easier than doing the casework, is you start with the string A, and you're sort of like constructing the string based on the information you have. So then you look at the position of B in the given string. If B is to the left of A, then you have to put it to the left of A. If C is to the left, because if B is to the left of A, then there's no way that you can put it to the right because you have to have that relative ordering. As it turns out, you only have to check A. The other characters don't matter because everything will either be on the left or right to A, because A is the first character. But you can also check everything if you want. Like for example, you can check if B is to the left of everything in your current string. So we look at this. Now we look at C. In fact, actually, it's basically, no, this is basically not brute force. It's actually, I don't know. There's not much of a brute force to do, so I guess I'll just talk about the linear solution. Linear in n, which is 26. So it's like O of 26 plus n, which is linear in both things because n is also almost 26. So first things first. Let fi be the frequency of character I, like how many times it shows up in the string. I don't think character has a dot. Frequency of character I. This is an N, not an R. Okay, so if any fi is greater than 1, like if we have any character more than once, then the answer is immediately no. And also, we must have some prefix of the characters. For example, we can't have A, B, and D. We have to have C in between. So to check that, we can say like we'll look at A. If we have A, if we have one of A, exactly one, then continue. Otherwise, if we have none of A, which is impossible, but like for an example, then we'll say that we're done, and therefore we shouldn't have any more characters that are greater than A. So then now we're checking to the right of A, and if we do have any other characters that are greater than A, because we don't have A, it's not possible that the string can exist. So essentially, another way to think about it is, if there exist like two indices, x and y, this is, by the way, like the fancy exist symbol. Basically just if for any pair x and y, like f of x is equal to 0 and f of y is greater than 0, then the answer is also no. Which is the same idea I was talking about, right? Because if we don't have some character, for example, say we don't have c, then we can't have any character greater than c, because by the algorithm, it means we stopped at c. So if we do have any, also x must be less than y. Sorry, that may be confusing. Yeah, x must be less than y specifically, otherwise this would be stupid. So if there exists x and y such that x is less than y, and we don't have x but we do have y, then the algorithm couldn't have constructed the string. This can be checked with brute force, or you can you can go through, if anything has 0 count, you mark a variable saying you're done, and then you check the other characters and you shouldn't have any of those. Either way would work. Again, the constraints are small enough to be very nice. So then, next part, we are going to, now we have to check if like the order of the characters matches. So we're looking in the string. It helps to store like a position array, like a position array where like pi is the position of I in the string. Essentially, we're going to start at A, and we're going to say this is our current string. Then we're going to look at B. We're going to look at the position of B. Now, it's only possible if either B is directly to the left of what our current string is, or B is directly to the right of what our current string is. And in that case, then we extend the string to include B. That is, we decrease the left by 1 or increase the right by 1, and then we continue. To do this, I'm maintaining variables L and R representing my current interval in my code. And then to check that, you just check if it's like directly adjacent. So now C must be on one of the ends of our current interval. If so, we extend it, otherwise it's not possible. Must be the same for D, and it is. So in this case, it's true. Say we have some other string, like for example, DBCA, yeah. So in this case, our current interval is A, then we go to B, but B is not directly on the end, it's detached from A, so it's not possible. There's no way we would have put C between B and A. So it's not possible. Then that basically determines the rest. If we have this interval, then everything works, otherwise it doesn't. Or like if it's always within an interval, then it works. And it's always to the left or the right of the interval. So the code is actually it's a lot more cases than I would have expected, which is kind of annoying. But so you read in the string, read in variables count and the position, then count is frequency. So, and also the position, just like setting those. It's okay to overwrite because if we have more than one character, we'll print no anyway. So it doesn't matter. We don't need like a list of positions. So this val stands for like valid. I could have done like pause too, but I already had this thing called pause, so I just used a different variable name. So for each character up to 26, and by the way, we're normalizing the characters, like A to Z become 0 to 25, just so like it's easier to work with in numbers. You can also iterate from A to Z explicitly. So if we have any frequency greater than 1, or we've concluded that we shouldn't have any more characters, but we do, then it's not possible. And if we don't have this character, then we shouldn't have any greater characters. Now we take the interval at the position of A. Now for each next character, if we don't have any more of this, then we're done with the string. And then we check if it's either directly to the left of L or it's directly to the right of R, and then if so, we extend the interval like so. And then if it's possible, print yes or no. So yeah, that's B. Also kind of caseworky in determining possibility. I mean, that's the whole problem, actually. Determine if it's possible. So yeah, okay. C, I don't know what this was. It just like, it was just a thing. Essentially, we have a list of lines in a file. So let's go through the first sample together, or let's go through the second sample. So we have a file with some lines in them. Initially, there are a certain number of lines. For example, in this case, there are 4. And then there's a sequence of actions done by each person. So there's person A and person B. A does actions 2, 0, and 5, and B does actions 0 and 6. So the actions essentially mean if the action is 0, add a new line. Otherwise, if it's not 0, modify that line. So what this means is, so for example, suppose we do operation 2. Then that means we're going to modify line 2. We're just going to do something to it. It doesn't really matter what we do. The only thing that matters is that line 2 must exist. So if I, for example, try to do operation 6, there is no line 6. So it's not possible. And yeah, so basically, we want to figure out a possible sequence of operations. And the constraint is that, like, we're going to take A's and B's elements and sort of interleave them. So for example, I'm going to use blue here. This is a time where color would actually help a lot. So for example, we know that this is the order that A did their operations. They did 2, then they did 0, then they did 5. Or they did 2 before doing 0, and they did 0 before doing 5. And B did 0 before doing 6, and we don't really know anything else. They could have done their operations in any order, just not at the same time. So for example, A could have done 2, and B could have done 0. Or A could have done 2 and 0, and then B could have done their 0, and then A could have done 5, and then B could have done 6. Or there could be some other sequence of operations. Maybe B did all their things before A did. Maybe A is a procrastinator like I am. So who knows? What you have to do is you have to figure out any possible sequence of operations that's valid, which means that no line is modified that doesn't exist, and it satisfies like this relative ordering that's given to us. So you have to find any such sequence of operations or say that there is none. That's basically this statement. So the way we do this is essentially modifying line X only works if we have enough lines. If it does work, then it doesn't change anything. So if we're able to do operation 2, then it doesn't hurt us to do so. There's no other constraint on the sequence of operations that we produce. We just have to produce any valid one. So because like it's possible for us to do this and it doesn't change anything, we might as well do it now. There's no reason that we shouldn't do it now, so we might as well do it now. And similarly for zeros, doing 0 automatically never hurts us, and it in fact helps us later on. So we might as well do a 0 now as well. But what about some operation that we can't do? For example, say we do 0, and then now we have 5 lines. But what about the 6? We can't do the 6. And that's okay. It just means that maybe either we'll do it later or we can never do it. But the point is, it never hurts to do an operation that we are able to do, which means that essentially we can do greedy on A and B. We look at A's current operation. If we can do it, then do it, and then continue. Otherwise, we look at B's current operation. If we can do it, then do it, and then continue. And if we can't do A's and we can't do B's, then, well, there's no operations we can do, so we're stuck. we've already done all the operations before, and we'll never be able to do these, so there's no way we could have ever have done them, and so it's not possible. Because also, like, the order of the operations doesn't matter. So, like, if we can't do them, then we'll never be able to do them. There's no sequence of operations in which we can do them. So essentially, we're doing greedy. At every step from A or B, we just take any move that's possible, and then if it's 0, we add 1 to the lines and we continue. So for example, here, what is going on? My neck feels weird. Yeah, stretch it some. So in code, this is how this greedy works. We read in the values. We read in A and B. I'm keeping a pointer for A and a pointer for B. And then, so if we have any operations left for A, and it's less than or equal to K. So either it's 0, in which case we can do it whenever, or it's not 0, but we have enough lines that we can do it. Wait. I think I kicked something, so I just want to make sure mic is okay. Good. If we have, sorry, I'm on edge since the last time, because the last video was bad. Yeah. So if we have any possible move that we can do for A, then we just push it to the answer. And then if it's equal to 0, then increment K, because it means we get a new line. And then also increment the position of A. We do the same thing for B, see if it's possible, update the thing. And if neither are possible, then it's not possible to do the whole thing. So then that gives us like the possibility check. So if it's possible, then we print the sequence of operations, and otherwise there's no way we could have done it, so the answer is -1. And we can't do anything. Cool. Problem D. Okay. Bitwise stuff. So this is more fun. Essentially, we have a sequence A. For example, let's take the sample. Let's take the sample 1, 2, 3, 4, 5, right? Yeah. Okay, and we're gonna write them all in binary. So, for example, we only need 3 digits here, one representing 2 to the 0, one representing 2 to the 1, one representing 2 to the 2. But this doesn't really matter that much. So 1 is 0, 0, 1 in binary, 2 is 0, 1, 0, etc. And now what we want to do is, yes, now what we want to do is, we want to take a new value. Alright, this is like a sequence A. Now, we want to construct a sequence B. And we want to construct it in the following way. So for example, say I have the sequence B of just 0, 0, 0, 0, 0. Then we're going to make a new sequence C. I'm gonna have to zoom out here. We're gonna have to make a new we want to make a new sequence C. So B in binary is simple. It might be easier to just write it out. Right, you get the gist. But we're going to make a new sequence C where CI is equal to AI XOR BI. And the XOR is essentially, the XOR of 2 binary strings is, it looks like this. So for example, say we have a binary string like this and like this. Then the result is, for each bit separately, if the 2 bits are the same, then we turn into 0. Otherwise, we turn them into 1. There are a lot more properties of XOR to go into, but none of them are relevant to this problem, so we'll save them for later. Or you can read up about them, I guess. XOR is some other cool things like addition mod 2, which means you can do some linear algebra and things like that. But anyway, this is a div 3D, so let's not worry about that. So in this case, 1 XOR 0, we look at each bit. These are the same, so it's 0. These are the same, so it's 0. These are different, so it's 1. In this case, this is 0, 0, 1, and it's 1. Now I'm going to make B a bit more interesting. Actually, no, it's fine. But like, anything XOR 0 is itself. So this would remain 2, this would remain 3, this would remain 4, this would remain 5. You can prove that if you want. Like 0 XOR anything is itself, as you can see here, and 1 XOR anything is the opposite of itself, as you can see here. So yeah, basically now what we want to do is, this is all introduction, this is just definitions. So now what we actually want to do is we want to construct a sequence C so that the sequence is increasing in their terminology. And the way to define increasing is we're considering like elements A1 and A2. Essentially, if we write A1 in binary and we write A2 in binary, then for every one bit that A1 has, A2 must also have that 1 bit. So this is called a super, or like, I won't use that term. So A1 must be a submask of A2, which means that like this is a bit mask representing A1. And so the mask that A1 has, that is every single one that A1 has, A2 also has that mask. So A2 is sort of like dominating A1. And so A1, this is called a submask. I'm going to use the terminology like is an element of. It's not perfect, but basically, just for this problem, this is the terminology I'm going to use. So basically, like A1 is a submask of A2. Every bit A1 has, A2 also has. And for example, in this case, this 1 doesn't matter because this is a 0. So this can be either 1 or 0. It doesn't matter. All that matters is that every bit A1 has, A2 has to have. So for example, if we had this would not be a submask because A1 has this bit, but A2 doesn't. And this is a submask because the property is true. So we're constructing B. We're constructing B, and then from that, we're going to take C. Now for C, we must have the relationship that the first element, actually I'm going to use 0, I don't know why I used A1. The first element must be a submask of the second element. And the second element must be a submask of the third element. And the third must be a submask of the fourth. And the fourth must be a submask of the fifth. And etc. to the end of the array, right? Sorry, I don't know what this is. It's disgusting. Just made it worse. Yeah, so this is the way that works. So C has to satisfy this property. You can also prove that it's transitive. Like if A0 is a submask of A1 and A1 is a submask of A2, then A0 is also a submask of A2 by default. But that doesn't really matter. We just have to have this relationship. So we need to construct B so that this is true. And we want to make it lexicographically minimum, which means the first element must be as small as possible. And then when the first element is small as possible, then the second element must be as small as possible while the first element is still as small as possible. So like the first element is the most important. Then making the first element as small as possible, we also want the second to be as small as possible. Then making the first and second as small as possible in that order. Then when the third must be as small as possible, and the fourth, and the fifth. And the reason it's defined, the reason this is nice is because the first completely trumps the second. Like, we always want the first to be as small as possible. And that means with lexicographic like minimal or maximal, it generally means it's some sort of greedy. We greedy on the first element. We make it as small as we possibly can because that's the definition. And then we greedy on the second element. We make that as small as we can. And then we make the third as small as we can, and so on. So greedy would work for this. So in this case, for any like initial element, what's the smallest first element of B we can have? In this case, it's 0 because there's no constraint on the first element. Like 0 is fine. So we'll make this 0 because 0 is as small as it possibly can be. So now C is 0, 0, 1, which is fine. Now for 2, what do we need to do? We need this bit to be filled in A1, but currently for 2 it's not, which means if we did 0, then this would be 0, 1, 0, and that doesn't work. So we need this bit to be 1, which means this bit here in B has to be 1. And what about the rest of them? Well, because this is the only bit we have in the previous element, we don't care about the rest of them. So we might as well make them 0 because we want it to be as small as possible. So now we take the XOR of 2 and 1, in this case it's 3, which is the bits 0, 1, 1. You can feel free and work that in your head if you want. It probably takes a while to get used to the idea if you haven't seen it before. So now for element 3. Well, looky here. We have this one already. We have this one already. So 3 can be 0, and it is. So in this case, this is right? Yeah. In this case, this can be 0, 0, and 0. And then this is once again 0, 1, 1. Now, here, this has none of these bits. So we're kind of screwed. We need both of them to be filled in here. So in this case, this has to be 3. It has to be 0, 1, and 1 here. So now the XOR is 1, 1, and 1. And then here, this has to be 2 because we need this bit to be filled. So this has to be 0, 1, 0. Now again, this greedy will work because that's just how lexicographic stuff works. There are some bitwise tricks you can do to make it O of 1, but it certainly works to iterate over the bits of a number, and then to just simulate this manually. If we have some bit in the previous element of C that we don't have here, then this has to be in the XOR, otherwise it shouldn't be, otherwise it would be otherwise it'd be larger than it needs to be. This would work. I'm not going to go over more bitwise stuff because this is enough for one session, but you can search up, for example, how to get the xth bit of a number and so on. But for people who are just looking for a nice formula, there's one other thing we can do here. In fact, there are multiple things we can do. We can use the formula representing what exactly we want. For the values we have to have in B, we want everything that's a 1 in A and a 0 in B. Or, no, sorry. We want everything that's a 1 in C, the previous C element, and a 0 in here. We can assume also, sorry, this should all be C. That could be confusing. Yeah. We can assume C of -1 is equal to 0 just for notation. For a base case. So we want all the bits such that in C they're 1 and A they're 0, and we don't want any of the other bits. So taking AI XOR CI minus 1 will give us only 0, 1, and 1, 0. So somehow we need to get rid of the 0, 1s, and the way to do that is to then AND it with A, or with C. Because then it will give you the bits that are not equal, and then we'll also get rid of the bits that are 0 in C but 1 in A. We only care about these. So this will give you the answer. There are other ways to do it. I used the formula, I believe it was AI and CI minus 1. It was CI minus 1 minus that. No, that doesn't seem right. Is it? Yeah, it is. Yeah. Minus is, yeah. Basically, it's everything here except for the things that are already 1 in both. So that also works. So the code's extraordinarily simple for all this like terminology and stuff. We read in the values. The current is like the previous value of C. Then we use either formula or whatever bitwise method you like to use. And then there's a good way to practice bitwise problems. And then we like take that, and that's our answer. And then this is how we maintain the previous element. It gets XORed with whatever the previous element was and the new answer we have. Cool. It's taking a while. I'm being very elaborate with these explanations because there is a lot to cover for D. There's a lot here. I don't know if this is the best suited Div 3 contest, but I guess it is. It's definitely educational, at least, is the nice thing. That there are a lot of things you can learn from here. Alright, in this one, you have an array. You have a bunch of air conditioners. So for example, here you can have an air conditioner with power 14, and here you can have one with power 16. Then essentially each air conditioner is going to affect everything to the left and right of it. It could be negative, I guess. No, I can't. Never mind. I don't know what I'm saying. Yeah. So now we're looking for the temperature of each individual cell. And the way the temperature will work is we consider each air conditioner separately. The effect that this air conditioner has is it lowers its temperature to the power of the air conditioner, or the setting of the air conditioner, I guess, which is 14. And then we add to that the distance between the indices. So for example, here, the effect of this air conditioner on this cell is 14 plus the distance, which is 1, so the total is 15. And the effect that this air conditioner has, the distance is 2, total is the value is 16, so total is 18. And then the temperature for a cell is the minimum over all air conditioners of the effects. There's also at least one, so the temperature is well defined. Yeah, so we want to find efficiently the temperature of each cell. Of course, we can do it in O of n times the number of air conditioners, or nk, but that would be too slow, so we need to be a bit better about that. So the way this would work is we're going to do a sort of common trick where we sort of break the absolute value. So in its core, absolute value is a piecewise function, which represents two things. If x is greater than or equal to 0, then it returns x. Otherwise, it negativizes x, and it returns negative x if x is less than 0, so that it's always positive. This is the definition we can work with. Absolute value is weird by itself, but what if we're able to break it? So the way we do this now is we consider the same formula. We consider the same box. But for this cell, we're only going to consider air conditioners to the left of it. We're only considering air conditioners to the left of it, or maybe on the same cell. So left or equal. Now, what does this do to the cost? So the cost for each air conditioner is T, so cell I, conditioner J. So the cost is Tj plus the absolute value of the difference in the coordinates. Of course, because we want the positive difference. But now we know, actually, yeah, AJ is the location, by the way. I'm gonna use the right terminology here. So this is AJ. But now we're only considering air conditioners to the left, meaning we know that I is greater than or equal to AJ. So Tj plus this difference can be simply represented as AJ minus I. No, sorry, other way around. I minus AJ. Now we're looking for the minimum of this over all j. So we note that this I has nothing to do with the selection of j, which means that we can sort of move it out. We can say that now we're looking for the I plus the minimum over all j of tj minus aj. And also aj is less than or equal to I. We have this constraint throughout. So for all things to the left of it, we want the minimum of this quantity. This can be done in a million ways. For example, you can use prefix minimums, because again, now we only care about this quantity, and this quantity is fixed for a certain air conditioner. It doesn't depend on the selection of I, meaning that just over all air conditioners to the left of this, what's the minimum of this quantity? And to do that, we can do like a prefix minimum, or we can do a running minimum, or etc. So that gives us 1/2. Now we do the same for the other half. For example, the air conditioner here. It's the same thing, except now the cost is, if I is less than or equal to aj, you can assume equal, it doesn't matter. If we count equal twice, it's okay because we're taking the minimum. So it's the minimum over all j of tj plus, again, the same cost, aj minus I, just the definition. Now, we know I is less than or equal to aj, which means aj is larger or equal. So it's the minimum over all j of tj plus aj minus I. Once again, we can remove the I. So now it's negative I plus the minimum over all j of tj plus aj. Again, only considering like the values where I is less than or equal to aj. Right? So we're looking for the minimum over some quantity of all values to the right. Again, can be done with prefix minimums, or like, I don't know, segment tree or something. There are a lot of ways you can do this. Now this is slightly different from my code, but this will work. It's linear time. And the way we can do it, the way I do it in my code is I'm doing the same idea, where we solve for only things to the left, and we sort of sweep left, and then we also sweep right. But the way I'm doing it here is, I noticed that basically every time you move one to the right, every air conditioner here, the effect will increase by 1, because now it moves one farther away. So basically, I'm maintaining the effects of every air conditioner to the left of here, or including it. Then when we move one step to the right, I just increment the effect by 1 for each thing. And that way, the effect increases by 1, and I'm showing that that happens. Because like it gets one farther away from each of them. And then we consider the air conditioners that are here, and then we take the minimum over all that to the left, and then we do the same to the right. Now I check the mic again. Very sorry before. Yeah, so in terms of code, set AI to some huge value initially, then process the air conditioners. A is just like the temperature of each cell. If some cell doesn't have an air conditioner, then it's just like, it's some huge value, like 2 times 10 to the 9th. Yeah, so we make answer. I guess it doesn't matter. I just have 3 arrays, so I need more than 3, so I just make another one. We sweep to the left, no, to the right. We maintain this running variable. Each step we increment r, meaning we get one further away. And then we do the same thing with going to the right. To the left, sorry, from the right. Yeah, that's the idea. Again, a lot of ways this can be solved. It's purely educational. But it's kind of nice because it showcases sort of like separating the parameters. Like we have a function of, sorry, I might go into this a bit more. We have a function of our current parameter I. That is, we're trying to minimize a function for this I, and we're trying to select a j that minimizes it. So if we can remove I from the equation, if we can separate the i's and the j's, then it's simply taking the minimum of a fixed quantity over all valid j. And that can usually be done with, like, for example, a segment tree or a prefix minimum in this case. Because here, j is completely independent from I. So I is its own thing. I is constant in this case. We're minimizing over I, which means this might as well just be some number, right? Like it's 2, for example. And then now we're just minimizing j And that means we just have to minimize this quantity, which is, again, a different number. It's just constant for j. So we're taking the minimum of these numbers. Okay. Actually, these are kind of nice. There are a lot of ways to do them. It's a lot like data structure, which I don't mind. I don't mind these types of problems. Okay. I did this weirdly. Yeah, so in F, you have an array, for example, 16, 24, 10, and 5. While all elements of the array are not equal, we're going to do some operations to it. In particular, in each operation, simultaneously, we set AI equal to the GCD of itself and the element in front of it. For the last element, it's a circular array, so the last element in front is the first element. So this is GCD of A0, A1. This is GCD of A1, A2, etc. And then this is GCD of A3 and A0. Actually, I might as well fill this out too. Right, so, sorry, I have OCD too. Yeah. So basically this is what happens after each step. So in this case, the GCD is the greatest common divisor. It's the largest number that divides both of them. So for example, in this case, it would be 8. 16 is divisible by 8, and 24 is divisible by 8. And there's no other number that's bigger that works. So in this case, we set this value to the GCD of 16 and 24, which is 8. We set this value to the GCD of 24 and 10, which is 2. We set this value to the GCD of 10 and 5, which is 5. And we set this value to the GCD of 5 and 16, which is 1. They share no divisors. Now we do it again and again until all elements are the same. And we want to find out the point at which all elements are the same. So in this case, this would be 4, this would be 1, this would be 1, this would be 1. In this case, it would be 1, 1, 1, and 1. So after 3 iterations, is it the same? In some other samples, it's different. For example, here, all the numbers start out the same. So it's fine the way that works. For 1, 2, 3, 4, 5, everything becomes 1 after a single step. For this, everything becomes 9 after a single step. And the main claim here is that at the end, everything will be equal to the GCD of the whole array. Everything will be equal to the GCD of all of the array values combined. That's the final value that will happen. Because suppose it's larger. Suppose the final value is larger than that. But then, like, how? Some element, if this is not the GCD, then some element is not divisible by this value larger than the GCD of the whole array. Otherwise, it would be the GCD of the whole array. So what about this? Then, because we only set it to GCDs, there's no way it can be larger. And there, in particular, there's no way it can ever be divisible by this larger number. So therefore, this value, whatever it is, can never become divisible by x, and so it can never become x, because x isn't a divisor of the value in the first place. So this shows it can't be greater, and we can also show it can't be less. Because, like, how would it be less? Right? The GCD of the whole array is this value. Which means that the GCD, like every single GCD that we could ever have using these array values, will always include this value g. Because it's always a divisor. It's a divisor of everything. That's the point. So the way this works is essentially like that. Like, the final value is this GCD of the whole array. Now this is nicer. Now let's make one more sort of observation. It's just sort of like an analysis of the way the problem works, and then from there that will give us the solution. Notice sort of what happens. Let's just look at A0 for example. Actually no, we kind of have to do the whole thing. So initially, I'm going to make these as far apart as possible. Initially, this is A0, this is A1, this is A2, this is A3. After operation 1, A0 is equal to GCD of A0 and A1. This is equal to GCD of A1 and A2. Actually, I'm gonna just use, I'm gonna stop writing A. I'm just gonna do 0, 1, 2, and 3. And you can assume I mean the array values by the indices. So this is GCD of 0 and 1. This is GCD of 1 and 2. This is GCD of 2 and 3. This is GCD of 3 and 0. Now, in the second step, this is the GCD of 0 and 1 and the GCD of 1 and 2. Note that 1 is included twice, but like every divisor of 1 is kind of already included, so there's no real reason to include it twice, so you might as well only include it once. And the GCD of any number of GCDs is still the GCD of everything, because we're again just looking for the largest value that divides everything. So in this case, you can show that this is equal to the GCD of 0 and 1 and 2. And etc. If you trace this out a bit more, which I'm not going to because I don't have space. Well, actually, it basically continues. This is the GCD of 1, 2, and 3, and then this is etc. And then after here, by the same logic, this becomes the GCD of 0, 1, 2, and 3. So after k steps, then A0 is equal to the GCD of A0 to AK, and etc. A1 is equal to the GCD of A1 to A of 1 plus K mod n. The mod n is important because it's circular, and then so on. In particular, it's equal to the GCD of some subarray. So now we're interested in the number of operations it takes for them all to be equal. So the number of operations it takes for them all to be equal is equivalent to saying, for how long is some element not equal to the final value? And we know the final value, it's this g. Which means we're interested in, for how long is some value not equal to g? And we don't care about what value it is, we just care about that there is some value. So we're basically asking, over all values, how long does it take before it becomes g? And then over all of that, what's the longest? And again, this will become first this, and then it will become this, and then it will become this. So it's always the GCD of some subarray starting at this. Meaning that now we've sort of reduced this problem to saying, what's the longest subarray with GCD greater than g? That's the final reduction. What's the longest subarray with GCD greater than g? And it works because if we take some like prefix of the subarray, like every prefix works because it has like fewer values, so the GCD is less strict. And if some subarray doesn't work, then every subarray after it doesn't work because it just like gets harder and harder. It's already g, it can't be lower. So what's the longest subarray with GCD being greater than g? That will be our answer. Now we just need to find it. So as I've sort of like indicated before, it's binary searchable because say we know the answer can be x, then every answer smaller than x works because the GCD is less strict as you have fewer elements. and say we know the answer cannot be like y, for example, then we know that this doesn't work because like as you stick on more elements, the GCD can only decrease. So if we find like the position where, if we find the x where like everything before x works and then everything after x doesn't work, then everything's cool. And we can binary search on this. I'm not going to go over binary search that much. It's also another concept you can learn. I think Ericdo has a really good video on it, so you can check that. I have explained it like various times. I'm not really sure. I think it's like varying degrees of... This is basically the condition you need. But this works. So now we're just interested in how do we do this. So for each index, we can binary search. Then we just need the GCD of a subarray. This can be done in also a lot of ways. For example, you can use a segment tree or a sparse table or something like that. Yeah, so that's how that would work. If implemented in a smart way, you can make the segment tree work in O of log of n plus log of AI. If not, it can be log squared, but actually no, it can't. Can it? Wait. Yeah, I think it can. I think if it's, wait. Now I'm confused. I think if implemented poorly, it could be made to be a log squared, which is bad because we already have a binary search, meaning it's going to be log cubed. I don't think it is actually. Anyway, I think a segment tree is log n plus log AI by some like magic, because again the GCD decreases every time, and because it decreases by a value greater than or equal to 2, it can only decrease at most log times. So yeah, and an iteration of the GCD algorithm will decrease it. So like everything works out there. Sparse table is just the log of AI. Everything works out fine. So in general, this is O of n times log squared of something. Doesn't really matter what, I guess. Yeah, there's another way to do it. You can do 2 pointers, where what I did was I made an array and then I created another array that's just the duplicate of the original array. Like for example, this is the same as this, this is the same as this, this is the same as this, this is the same as this. And the reason this was nice is because it handled the circular part easily. So we can do 2 pointers on this array and not worry about the circular part. And if the answer is larger than n, like for example, if every element is initially the same, then the answer would be larger than n. And in this case, you can just set it equal to n. Like take the minimum of the answer in n. So you don't, because of course it can't be larger than n. So we do 2 pointers. And this uses another trick. It's called like a monotonic queue or something, although not really. It's basically, it's the same idea. If you know sliding window maximums, that's the thing you can look up. Basically, it will do it in, it will let you like maintain the maximum of an interval where you can add an element onto the end or remove the previous element or remove like the last element. So basically it lets you maintain a queue and you can find the maximum in that queue. And it works for like basically any function. So GCD would also work here. So this would be, because 2 pointers is linear, and this is a log from the GCD, you get O of n log, I think it can be made to work in that complexity. Yeah, I think you can, I don't know, you can probably force it to be in that complexity. I don't know, maybe it's better. But it'd be like n times log of AI in this case. So yeah, that would work. A lot of things would work. Again, a lot of things. Final part. I don't like these problems. They take a while to explain. Like that. And the longer they take to explain, the more chance I have of my mic cutting out. So, last problem. This one's nicer, it's just graphs. There's no like introduction, there's no stuff to prove. Basically, it's just graphs. We're given this graph. I'm just gonna steal this. This is nice. We're given this graph. We're interested in some like statistics. We're interested, we start at 1. We're interested in the number of paths we have from 1 to every other vertex. So for example, we can even print the mod 189 plus 7, I guess, but I don't know why they stopped here. They could have us do mod and it'd be like slightly more annoying, but not even that much more annoying. Or maybe it's hard to do mod, I don't know. Anyway, we're interested in the number of paths from 1 to each other vertex. So in particular, it can be 0 for no paths. It can be 1 for 1 path. It can be 2 representing any number more than 1 path. So for example, we can have exactly 2 paths like this, or we can have maybe another edge like this that's like 3 paths, or we can have like a billion paths or whatever, right? Or like 2 to the 30th, or 2 to the 400,000, for example. Although a bit less than that, but like an order of magnitude off. But the point is, we can have a lot of paths. Actually, like more like 2 to the 200,000, but I digress. So 2 represents more than 1 path, and then -1 is infinite paths. And the point here is that paths can repeat vertices. So for example, like this graph would have infinite paths from 1 to everything. Because for example, suppose we're looking for the paths from 1 to 2. We can start by taking this, or we can take this, or we can take this, or I think I did it. I think I overdid it, but we can take that. Like we can go through the cycle any amount of times, and we can just keep doing that. Okay, so yeah. So the way this problem works is it's basically I think it's required to use strongly connected components here. So basically we make this like condensation graph where every strongly connected component, which by the way, if you don't know about those, you should learn those sort of as a prerequisite. I don't know if it requires them, but that's what I know. That's how I know how to solve it. So let's make a better graph. For example, like this. Yeah, and then maybe like this. This should cover all cases. It's kind of complicated, but I think it covers everything. There's a node here. Should have drawn the node first. Okay, I think this covers everything. Hopefully you can tell how the arrows are. So essentially, here are the values for this graph. This is node 1. So the answers are, it has 1 path from 1 to 1. This has 0, this has infinite, this has infinite, this has infinite, this has infinite, this has 1, this has 1, this has 1, this has 1, this has 3. And so the answer is 2. And so the condensation graph here would be, everything would be the same, except this would be a single node, like a strongly connected component. Now, if a strongly connected component has more than 1 node, or the other case, it has an edge to itself, then there are infinite paths, assuming we can reach here from 1. And the reason we have infinite paths is because, like essentially we always have a cycle, so we can just keep going along that cycle as many times as we want. So if we have any SCC that has a cycle, either an SCC or something that has an edge to itself, then there are an infinite number of paths. And otherwise, essentially now that we've condensed the graph into like showing connected components, now we have a directed acyclic graph. You can feel free to redraw this out if you want, but I'm not going to redraw the whole thing just for a single node. Actually, I will, just to get the point across. But that's basically how that works. You can leave most of it intact. Essentially, now we get this new graph. How did I miss that so badly? Where this is that, this is the new node, and everything else is the same. You see, basically the same graph. So now all nodes on this SCC have infinite. This has still 0, this has infinite now. And so now basically we're doing like sort of a DP-like fashion on this directed acyclic graph, where initially 1 has one path. And then if it's in an SCC, then we set its paths to infinity. So in general, we track the number of paths going in. We order in like topological order. It's like standard directed acyclic graph like DP. So we're iterating in topological order in any of them, doesn't really matter which. Then we say initially each node has 0 paths to it. Now, this is the order we're going in. So we're processing some node. For example, say we're here. If this node is 1, then it has at least one path. Then, in this order is important, then we check if it has infinite and at least 1, then it has infinite. If it can't be reached from 1, then it still has 0 paths regardless of the fact that it's an SCC. And so the way we check infinite again is either it has an edge to itself, like we have a node that has an edge to itself, or we have an SCC with more than one node. And in fact, I think these are equivalent because like an SCC having an edge to itself, like if it has more than one node, then it would have that anyway. So we might as well just check if it has an edge to itself. Like if there's an edge from some node in the SCC to some other node in the SCC. But it doesn't really matter. The point is we just check if it's infinite. And if so, then it's sort of like a special SCC. And otherwise, every other SCC has to represent only one node, because otherwise it would have 2 and it would have a cycle. So if it can be reached from 1, that is, if it has at least one path already, or it has infinite paths, and this is in a special SCC, then it has infinite. So in this case, for example, say we do have this SCC, which is a cycle, but it can't be reached from 1. So even though it is a special SCC, it's still 0. That's an important distinction. Then afterwards, now we know the number of paths. So now, in the DP-like manner, we push out the number of paths from here to every other node it can reach. I will answer that later. I'll answer that after the recording. Okay, basically, yeah, so here we push out the number of paths from here to everywhere else. Are we fine? No, I'm insecure about the mic again. Yeah. We push out the number of paths from here to every other vertex. And like, we say that like, we have this many paths here, and we can go from here to here, so now we also have this many paths from here going to here. So in this case, if we have like dp of x representing the number of paths to this SCC, then if we have the edge x to y, then we would eventually do dp of y plus equals dp of x for each y outgoing from x. Or in particular, we can say that dp of y is equal to the sum over all x that have an edge to y. Or in particular, over all edges x to y. It's the sum of dpx. If it's infinity, we treat it as infinity. If it's greater than 2, then we just take the minimum of 2 and like the real number of paths, and that works because that like prevents overflow. And we only care about having at least 2 anyway. It's just more than 1. So that works. And basically we do this DP in topological order, and that gives us everything. So we just need to like handle infinity well and stuff. So the way this works is essentially we read in N and M. We clear a bunch of stuff because multitests. We create an SCC. In this case, I have a template for it. We're reading in X and Y, adding the edge here, adding the edge into the SCC. We create the SCCs. Now we mark the component of each vertex, which is this array C. This AI represents the DP, and the BI represents the in degree, which is how I'm doing topological order. I know that SCC also gives you topological order sometimes. It doesn't really matter how you do it. But yeah, now we add the edges in the condensed graph. So instead of adding edges from nodes to each other, now we're adding edges from SCCs to each other. So in this case, maybe we have this edge to itself. In this case, we don't add to the in degree of this, otherwise it's pointless. It will mean that we never actually visit it. So if for each edge in the initial graph, if the SCCs are the same, then the SCC is special. And that means that it will have infinite paths. It has one cycle in it. And otherwise, we add the edge in like the condensation graph, and then we increment the in degree. Then we're doing topological order. We just keep a queue, and then we in the queue we only have nodes that are in degree 0, and then when we process a node, we decrease the in degree of everything that it has an edge to. So now, if this is 0, or if it's in the SCC with 0, then it has at least one path. If it has infinite paths, then set it to -1. Then for each outgoing thing, if either of them are infinity, keep it at infinity. Otherwise, take the minimum of 2 and the number of paths. Then topological sort. And then the answer, like each SCC has the same answer. Like every node in SCC has the same answer. So we just print the answer for that SCC that's in. So again, we're doing this DP on the condensation graph because then it's a directed acyclic graph. Like the condensation graph where every SCC is compressed into a single node. And yeah, that's the idea. It's fairly standard, I guess. I'm not good at implementing these kind of things. I never have been, so yeah, that's just kind of how it is. Still 9th. That's cool. Yep. Awesome. I don't think I have more to say. So send help as always. I did the sub count, right? Yeah. Okay. I think we're good. I think that was everything. That was all the problems. In terms of like overall like commentary, this was a bit more difficult than like the previous style of div3s, but it was also the same amount of standard. So I don't really know which I prefer. I usually do better when the problems are easier. So I prefer the problems to be easier. That was the only time I won the round, but whatever. I guess this is fine. It's an okay first round. I guess we'll see with the hacking phase. I remember with one of the previous div3s, there were validator issues where like there were 2 independent problems where like you could have inputs that were invalid and it would totally break everyone's program. Like for example, it said like n is up to 10 to the 7th, and then it would let you do like n equals like a billion or something, and of course that would cause like runtime errors and things like that. So that wasn't nice. But I guess we'll see here. They do have a lot of testers, so I hope everything works well. People upsolving already? Yeah, okay, I don't have more to say. Hope you enjoyed. Goodbye.